Morning, guys. I'm just going to do a quick lecture on the 8.4 chapter, which is entitled On the Road. Now, this one and indeed 8.5, which is titled Vehicle Safety, are quite straightforward and just require a bit of reading through the textbook on your part. There's not very much hard physics in this, but I did just want to draw your attention to a bit of a recap on thinking distance, braking distance, and stopping distance. And we did talk about a bit about this before, but I want to just recap. So, if you remember, we've got the total distance that a car needs to stop. We've got a stopping distance, and that's equal to your thinking distance plus your braking distance. And at GCSE, we were fairly happy with that, and you can just describe different things that would affect it. So thinking distance will be things like alcohol consumption, drugs, whether you're tired, the radio, CD, window open and stuff. And then your braking distance would be things kind of what's wrong with the car, if your car's been serviced, the tyres, the friction, the weather conditions, that kind of stuff. But in A level, we want to look at the physics and what actually is going on here. So during our thinking distance, say we're just pootling along at a constant velocity, and we've got our just normal SUVAT SUVAT. Normal velocity, so that's going to equal U. Our velocity is not going to change during our thinking distance. It's just it's the distance that our car travels while we're thinking about braking. So the acceleration is going to be 0, the S is going to be S, and we've got T. So it's just a simple speed equals distance over time. So speed, which is U, or V in this case, we use V. Speed equals distance over time. So our distance equals Vt. And that is our thinking distance, S. Now, our braking distance, again, we've got SUVAT. So we're going to go with distance S. We're going to have our initial speed U. Our final velocity is going to have to be 0. And we're going to have an A, and we're going to have a T. So we're not really interested in the time in this one. So let's just see what that brings out. So we've got V squared equals U squared plus 2AS. Now don't forget, if we've got our car and it's going that way at speed U, and our acceleration is going to be that way. So our equation can be V0, so V equals U squared. Because our acceleration is 0, that's going to be minus 2AS. So then our U squared would equal 2AS. So our S equals U squared over 2A. And that is our braking distance. Now it comes out as exactly what you think. The better acceleration of the car, the better deceleration of the car, the shorter the shorter the braking distance. However, here you have a very interesting conclusion. So stopping distance, we can add these two equations together to get our total stopping distance. Is equal to, I'm going to use u again just because it's easier from the stop equation here, equals ut plus u squared over 2a. So it goes up on u for the thinking distance and u squared for the braking distance. So let's just look at some sample data. So let's do a little table. We've got thinking and braking. If I just move them over a bit so I can tell you what speed we're going at. And then total. This is average time it takes. So this table is just going to take a couple of things into consideration. Obviously, we're going to use an average thinking time and an average deceleration of a car. So we look at it at 30 miles per hour, 50 miles per hour, and 70 miles per hour. Thinking time kind of goes up quite linearly. 30 foot, 50 foot, 70 feet. Braking distance, 45 foot, 125 feet, 245 feet. Which is total stopping distances of 75 feet, 175 feet, and 315 feet. Or if you like meters, 22.5, 52.5, 94.5 meters. So it's quite stark that if you double your speed, you're more than doubling your stopping distance, and that's why there are things like 20 miles an hour speed limits, because you can stop almost in half the distance just by reducing your speed. I'll leave you to read pages 146 to 148 in the textbook, just so you can get your head around this. Next thing I want to look at is 8.5 vehicle safety. With you. So, how can we use physics to make vehicles more safe? Well, what I'd like you to think about is one of the main equations that we use in physics, which is work done is force times distance. So that play a massive part. So you've all heard of like G's, and cars can have so many G's going around a corner, and astronauts feel so many G's in a collision. Now we can express this force in terms of G's, right? And we have that in a deceleration. So say for example, we work out that a car's acceleration is minus 30 meters per second squared. That would be the same as saying roughly that's 3 G's. It's technically wrong because it's not an impact force, but it's a good way of discussing. Um, something that we do need to look at in this part is that we need to remember that force is the rate of change of momentum. So, if we look here, we can change the amount of force that you feel by changing the impact time. So if we for a fix, if we fixed your mass and velocity of the car that you're travelling, so that's obviously going to be fixed. But if we can find a way of increasing this impact time, then that will have the effect of reducing the force. Which is what it's all about, and that's what everything in a car to help you happen. So I mean, airbags. What does an airbag do? So I mean, an airbag just increases the time of the collision, right? I mean, this might be quite a strange concept to you, but I mean, you've all been travelling in a car at 70 miles an hour, right? Down a motorway. Got a car going at 70 miles an hour. That's a really rubbish car. Hang on a second. It's a car going, that puts some wheels on it. Look. Car going at 70 miles an hour, and eventually, at some time t later, that car gets to 0 miles per hour, right? Say you go up to a roundabout or go down a slip lane or something, or some traffic. Gets to 0. What force did you feel? Well, the force you felt was the change in momentum, which is the mass of the car, times the change in velocity, divided by the time it took. Now, the time that it took for you to go from 70 to 0 was probably like 20 seconds, right? So which means that force is quite small. Now you try going from 0 to 70 in like 0.5 seconds. What about going from 0 to 70 in 0.1 seconds? You can see that if you went from 0 to 70 in 0.5 seconds, that would actually be 40 times the force from doing it in 20 seconds. So you kind of see how this works. So we need to increase the impact time. So, but I mean, also using Suvat, we can go ahead and work this out. So. But first of all, I just want to make you aware of the difference between two words. You've got contact time and impact time. So, if objects collide or bounce off each other, they are in contact for a certain time, right? So if we've got car A going this way, and we've got car B going this way, and they impact and they collide and they bounce off each other, there's a certain time that they are in connection with each other or in contact with each other, and that's the same for both objects. And as we've said, shorter the contact time, the greater the force. That's my mobile phone. Hang on a second. So, sorry about that. So the contact time is how long they're in contact for each other, and the impact time is how long they are so the impact time is the time until they are moving at constant velocity, at the same velocity as each other. So the impact time is time until they're moving at the same velocity. And the reason we have to make this distinction is because objects, say, I don't know, if we have car A again going this way that hits car B and they move off together, then you could say they're in contact for, I don't know, a minute. But the impact time is only until they are moving at that constant velocity. So that's the time that you need to take for your force calculation. I hope that's clear to you. Sorry about my phone, by the way. So this has been just a quick run through of stopping distance, and vehicle safety and on the road. Any questions, please do get in contact.